But we will see that solid-state batteries is a subject today that I think often experiences very high expectations. And I think that these, I hope that during my presentation you will see that many of these are really expectations that have yet no serious proof, I would say. And let's see. And we will start very much with lithium, because there is lots of research, and particularly in my group, lots of research on lithium solid-state batteries, and will then move slowly and transfer into our post-lithium ions. That's why I called it post-lithium perspective. So I think we discussed that also on the way to our POLiS 2 proposal, whether the title is still good. Post-lithium somehow suggests that there will be something after lithium, and I think this is definitely wrong. I think we should speak about beside technologies. There will be side-by-side technologies and not something that will completely replace lithium. And I think, yes, in this paper by Yuri Gogotsi, there's a very nice graph in this Ragone chart. We see power versus specific energy. And I magnified this part where you see there is, I would say, the little world of current and potentially future battery technologies, at least I would say in the short and midterm perspective. You see this this green shaded area is lithium-ion batteries. Somehow, you see on the next slide, we will see where that limit is, about 400 watt-hours per kilogram. And at the bottom side, sodium is coming closer and closer and is endangering perhaps lithium. I think it depends all on the cost politics and price politics of the Chinese at the end. And at the upper side here, you see the solid-state battery, which supposedly may provide high energy and high power density solutions. To make that short, it will require the use of the metal electrode, the metal anode. Otherwise, these numbers, I think, cannot be achieved. And of course, electrolytes with very, very high conductivity. We'll see what that means. Conductivities that really go beyond 10 millisiemens per centimeter, so that you can really create thick cathodes. Maybe even if you use at the anode side, not a metal, but something else, also thick anodes, in order to achieve really your high capacity and high energy targets. Well, a few years ago, so this is from 23, Hong Li, who is really one of the battery, I would say, enthusiasts long-term in China and Chinese Academy of Sciences, published a paper where they published 500 watt-hours per kilogram, which is really a very high specific energy. And the question is, how solid is it? And in fact, it's a completely liquid-based battery, liquid electrolyte. I will not go in details. And they even went up to 700 watt-hours per kilogram. Now, what you see here is now the specific energy. I think they misprinted that here in energy densities. In fact, the mass-specific energy is a function of year. You see, this red limit here is something you can only surpass that if you really include a lithium metal anode into your cell. So this is the limit that I would say separates the graphite world from the lithium metal world. And they went up here, so you see Jeff Dahn also did that. And this cell with 700 watt-hours per kilogram and energy density of 622 watt-hours per liter only made 3 cycles. It was created to show what you can achieve with density, but it did not operate. So I think that's somehow, there's no impedance spectra, and they said themselves this was designed only to show energy density and specific energy, but not operation. So that's, of course, then I think it shows that the limits of liquid cells are still not achieved, and that, of course, liquid-based batteries and the lithium-ion battery is a benchmark that is always the white elephant in the room. We always should know that. There is a well-working cell system. It's not yet that good here, and I'm not sure whether they really can operate. I'm pretty skeptical whether a lithium metal anode can ever operate safely in a liquid environment. So this is one of my, I would say, beliefs that I think this is very critical. I'll see. So successful operation, that's then my credo is of a lithium metal anode, and sodium and potassium, I think requires at least partial solidification of the battery cell. You need, I think, really a solid electrolyte wall. Now, and so the full picture, I would say, of all the different types of batteries, we would be at the left side, the lithium-ion battery, with the blue background is the liquid electrolyte impregnating the anode and the cathode, and the, let's say, the target, the ultimate target would be a true solid-state battery where there is, in fact, reservoir-free, so that all the alkali metal is produced during the first charge here. There's a separator, and there's all true solid-state. When the first solid-state batteries, inorganic solid-state batteries came up, people, I think, were suspicious, thought that Toyota added a few drops of a liquid in order to improve the contacts. There's always contact issues. If you go from here and jellify stuff, then you come to something like semi-solid-state batteries. But still, these batteries, and often Chinese solid-state batteries or gel-type batteries, still contain 10 to 15% of liquid electrolyte. Now, Felix Richter, who is also part of the wider POLiS faculty, I think created a very nice paper, and yeah, I think on the topology of battery cells, where he said, okay, let's distinguish the different types of electrolytes that can be used in a battery between anode and cathode, between on the basis of the conduction mechanism. The conduction mechanism is electrolyte, jumping ions is different from liquids and from dry polymers, and in between we have all the hybrid materials. And that also made him to set up a list of potential cell types, all reservoir-free or anode-free, with a liquid electrolyte or a dry polymer or a plasticized polymer electrolyte, which is just the one electrolyte in the cell, or a true inorganic solid electrolyte here. So these are different types of electrolytes. Or you come up with mixed hybrid part and matrix electrolytes, or a multi-layer electrolyte, which I think comes up when we use electrolytes that are not stable at both electrodes. Then we have to use a bilayer type cell. Okay, and this brought us to a roadmap for solid-state batteries, where in principle somehow we made the same and said, okay, there is of course oxide type, sulfide type, halide type, polymer type, chemistries for electrolytes that create of course quite a number of different cell types. But I will concentrate in the following mostly on these sulfide type cells, and you will see why. Now, the last, I would say, decade showed lots of industry interest in these solid-state batteries, despite the fact that there is, I would say, still not the ultimate commercialized solution, but it shows there is lots of hope. Just remember this little plot or this little graph from Gogotsi at the beginning. There is the lithium-ion battery, and either you come from the sustainability bottom end with sodium, or you come from the high performance end with a solid-state battery. This is the little world currently. And POLiS, of course, will attempt to add more to that, to open more alternatives maybe for other specific applications, and to see whether other ions can be used in a useful, in a sensible way. What are the remaining challenges of solid-state batteries? And there is quite a few, I would say. If we take this cartoon here for the cathode composite, where now the active material is mixed up with a yellow electrolyte. We have a separator electrolyte, and these particles already, I think, suggest that this is inorganic. So we have, of course, also the problem of compacting powders. Particle technology is an important point. And here's then the anode. And all the interfaces, in fact, are critical. Stack pressure. Most of these batteries operate at very high stack pressures. And we need to go down, of course, to essentially 1 bar. Not more, 1 to 2 bar. Otherwise, at least the car producers will not make use of your battery. And if you have to use tons heavy press cells to operate your battery, that will make no sense. Chemomechanics is, of course, an issue. Safe cell operation safety has yet not been, I would say, fully proven for large solid-state batteries. Upscaling and cost is an issue, and of course materials availability also for the electrolytes. And also finally, scientifically, I think understanding the role of the microstructure, we see that in one example at the end, charge transport and interfaces. There is lots of fundamental issues left. Otherwise, I think we would not be interested in the subject as such. If it would only be technology, that's not the case. Okay, let's look a bit into solid electrolytes. This is from a lithium map where you see for sulfides, oxides, polymers at room temperature and at elevated temperatures. And there's two simple criteria. If you want to use an electrolyte in a cathode, as a solid electrolyte, there's modeling studies that you need at least 10 millisiemens per centimeter. Otherwise, it will not be competitive. Of course, you will have a battery, but it cannot compete with a lithium-ion battery at the end. The separator, I think there the limit is less strict. 0.1 millisiemens per centimeter is enough. If you have thin enough separator, you don't lose too much voltage there. And you see, quite simple, there's only sulfides in the inorganic world surpassing that, and essentially yet no polymer that really makes that, no dry polymer that makes that. If you plasticize polymers, you can, of course, go up with the conductivities. But that's why the sulfides play such a big role. And Wolfgang Tsai and me, 2 years ago, we created this graph where we show all the, let's say, lithium electrolytes. Be patient, sodium and potassium will come in a second. You see these green lines are isoconductivity lines. Here's the charge carrier density, as you would, as a semiconductor physicist would plot the conductivity of semiconductors, charge carrier density, and mobility of, in this case of lithium ions, the product gives conductivity, of course, times charge. And you see here is the liquid electrolyte cloud, and here are the inorganic solid electrolytes, and only the sulfides climb up here. Of course, the liquid electrolytes meet the 10 millisiemens per centimeter total conductivity. The lithium ion conductivity is less. It's about 4 millisiemens per centimeter. And here are the polymers. So that varies, of course, very, very much on the degree of, or let's say on the fraction of plasticizer in the polymer. Well, inorganic chemists are really clever, and so the conductivity climbs up. Oxychlorides also make it. So I think there's lots of improvement over the years. Of course, this may be, I would say, a sustainability or a cost axis, no? Because lithium ions cost money, and it may be that a substantial amount of lithium ions is in your electrolyte, where they don't contribute to the charging process. They transfer, but they don't charge. No? So this is, no, this is of course not an issue with sodium. No? Sodium is cheaper, so this is the sodium map, and this is something we prepared for the POLiS book, which I think is yet still, I would say, on the way to come. So a chapter on electrolytes, I will be happy to get input on that. So Ronja Haas collected all the sodium data. We see also here the sulfides are good, and Felix Schnaubel in our lab, I think he is very optimistic to make thio antimonides to design them such that they have conductivities even climbing above 100 millisiemens per centimeter, which I think is, of course, then extremely high, ultra high conductivity that would offer allow very high, very thick cathodes. And here the liquid electrolytes and the polymers. But if we go on with our post-lithium ions, potassium, of course, already looks a bit poor at the anode, at the inorganic side. There is sulfides, but just climbing up to 10 to the minus 4, so there is more to go. And I think there is the potassium beta alumina that is not too bad. But as you see, as in the case of lithium and sodium, the high conductivity of inorganic materials comes at the cost of a higher ion density. So we need always many more ions to achieve the same conductivity as the liquid electrolytes. Liquid electrolytes are a great thing. That's why we, I think, use in electrochemistry since 220 years, liquid electrolytes. And magnesium, I would say there's Clarissa from our POLiS team who really, I think, recently published the highest conductivity for a magnesium solid electrolyte, which is a magnesium ytterbium selenide that goes up here into the direction of the 10 to the minus 4 Siemens per centimeter. But of course, magnesium divalent and potassium divalent have, of course, really serious issues in the solid state. That's why we also suffer from proper electrode materials and not only from solid electrolytes missing. That's conductivity, but of course another issue, they have to communicate properly with electrodes, with the negative and the positive electrode. And there's stability issues. Right? Let's discuss that here again for the case of lithium, but it's the same for sodium and potassium. We have very high lithium chemical potential that will then reduce our electrolyte by transfer of an ion and electron at the cathode side, at the positive side, we can have oxidation by delithiation. Always remember, if you see pictures like that, I think good enough, publish a paper where you only discusses electrons. That's, of course, not complete. You always have to transfer an ion and an electron. Otherwise, you charge up your interfaces and that doesn't operate. So the pure semiconductor picture is not enough. You need also to include transfer of ions. So the original good enough picture, I think, is incorrect, and always take care of that. And again, for the case of lithium, let's just quickly go through here. There's the various materials. And in a nutshell, we can say, okay, at the negative side, for lithium at least, only be some polymers, but particularly the oxides, a few oxides are really stable. And at the cathode side, halides may be stable and oxide may be stable, but we have serious stability issues, at least when it comes to these top sulfide electrolytes. No? They are easily oxidized and easily reduced because the stability window of a thiophosphate with phosphorus 5+ and sulfur 2- is only 0.5 volt. And we have to protect the interfaces. This is qualitatively the same for post-lithium solid electrolytes. For sodium, I would say it's everything quite the same. Okay, now one subject from our research lab, and I told you in order to really have competitive solid-state batteries, we need to operate an alkali metal electrode. Let me speak of not lithium, but alkali metal anode. And as you will see at the end, lithium, sodium, potassium, we try all three in principle. Nevertheless, we started with lithium. And one of the important things is, as we found, the microstructure of the alkali metal. I'm not sure whether you ever thought, okay, what is the microstructure of a metal? That depends a bit on your background, whether you're a material scientist or a chemist. If you're a material scientist, you will know everything about dislocations, grain boundaries, and all the microstructure of a metal. The question is, what is the role of that? Now, Till Ortmann, so I stole these graphs from Till, also presented here several times. If you have now such a cell with a metal anode here and a cathode here, during dissolution, of course, the metal has to be dissolved, and that means the metal atom has to migrate to the electrolyte, is being oxidized, and leaves a little vacancy here. And this vacancy has to be refilled, otherwise you have an elementary point contact loss, I would say an elementary loss of contact by a vacancy. And only if the vacancies in the metal are fast enough, if diffusion of metal is fast enough, you restore your interface. And if that is not the case, you will simply create pores. And this pore formation is a very important issue in batteries. You have contact loss and then pore formation, and this is what, of course, Till in his PhD thesis observed. And I think he was really the first worldwide to publish, I would say, results on these sodium metal electrodes and their properties on stable oxide solid electrolytes. Now, during plating then, if we charge, in principle, we should, of course, then deposit homogeneously metal, but once we form pores already in the first step, we have only a few contact points, and this is the starting point then for dendrite formation because we have current focusing at these few contact points. So that has to be avoided. So any pore formation is really critical for the later formation of dendrites. And okay, now you see the metal is here, just a homogeneous gray phase without any substructure. But there is, of course, a structure. But what is the role of the microstructure? In fact, and that is something that has nicely been shown by theoreticians, not only the electrolyte has a structure by grain boundaries, but also metals, of course, have grain boundaries that will influence, in fact, the diffusion of these vacancies and influence, of course, also the mechanical properties and the stress-strain distribution. So the microstructure of the alkali metal, not only of the solid electrolyte, is really critical. And Don Siegel, in fact, calculated that the diffusivity of alkali metal in grain boundaries can be up to a factor of 10,000 faster than in the bulk. And if this is the case, grain boundaries, of course, play a major role. So one could think of, oh, let's use a nanocrystalline metal to make it faster. But of course, the problem is that this diffusion also is responsible for ripening of grains. So there is, I would say, really a conflict in targets. And they calculate, in fact, the role of the grain size, and you see, in fact, that in principle we can achieve much higher and fast charging for very small grains of metal. And the question is, can that be achieved? And I would say very, very difficult. We would need metal grains below 1 micron. And that was the point where we thought, okay, but how to see the microstructure of alkali metal, of lithium metal, of sodium metal? Nobody really properly did that, and that was the starting point for work we did here also in the POLiS cluster and by Till Ortmann, Till Fuchs, showing really the microstructure by electron backscatter diffraction, establishing a workflow, to make that story short, to really establish a complex workflow in our labs where we are able to cross-section an electrode, plated lithium, plated sodium, plated potassium, and image really the grain structure after plating or after stripping. And what we saw is, in fact, that all these alkali metals grow really in huge grains, with almost virtually all grain boundaries are vertical. It looks like a row of teeth. And in fact, they ripen essentially very fast. So this is the sodium case here. You see huge sodium grains, bigger than in the case of lithium. So lithium on garnet, lithium on a sulfide. But this is, of course, the case that interests us within POLiS. Huh? So the sodium growth and dissolution, that's something we go on. And Till, just to show the series here, managed, in fact, to not only observe that in the SEM, essentially live, but also see where are pores coming up. And what you see here is all the homogeneously colored areas are single grains of the metal. The pores are formed in the grain, not in the grain boundary. Typically, one would think that pores form at an edge pit of a grain boundary. No, but the grain boundaries are faster. That's why if you take out there an atom, it's quickly replenished and quickly refilled. That's why pores are formed primarily in the grains, not in the grain boundary. The grain boundaries refill very, very fast. And so there's much more work, and due to the constraints of time, I will not go into detail with that. But meanwhile, Rebecca also worked more on lithium metals, where he really showed then nicely how if the layers get thicker and thicker, up to 100 micron thick lithium films and sodium films, the grains grow bigger and bigger. And in fact, that's reversible. If you thin it by stripping, the grains get smaller again, because that is all controlled by grain boundary and interface energy. So really nice. And we came up with a model for plating and stripping of these alkaline metals. So there is much more to that. But let me come to a very final point, not to stress you too much. And that is a bit more on sodium metal and potassium. In fact, Till, what you see is, of course, something you don't like to see. So this is a sodium claw coming out of a little electrode that is patched on a sodium solid electrolyte, grew out. No nice homogeneous growth, but something like dendrite and bisca growth. In fact, what we currently investigate is really nucleation of sodium, of lithium, and in principle also of potassium under these current collectors, how we can control them. And you see with higher current densities, you get much more homogeneous nucleation. This is all in detail being studied, how the number and size of nuclei, of sodium nuclei, change with current density. And the nucleation peak here and growth very homogeneously, works very nicely as a function of current density. There is no so here's the nucleation, and here's nice growth without dendrite growth. And in fact, sodium at room temperature can be nicely plated and stripped with higher current densities than lithium. Stable potential drain growth. And this even can be observed by optical microscopy. By confocal microscopy, you see pristine current collector observed from top. And then with increasing current density, more homogeneous growth, as you also see here, less pores. And we go on with that. And in the cross-section, of course, you see nice sodium layers formed here. Okay, and the final thing I would like to show is, in fact, that we went on. Max Wacher is brave enough to even bring that to potassium. So what you see here is potassium really grown under a copper current collector on a potassium beta alumina solid electrolyte. Remember, potassium has a melting point that is short above room temperature, but it works very nice. And you see here for the crystallographers in POLiS, this is lithium, sodium, potassium BCC with the EBSD works nicely. And this is essentially a single grain of potassium being grown on the solid electrolyte. But point is, of course, and this is the final thing I would like to show, one more little thing. We wanted to see that with a dilatometer. So we set up an operando dilatometer where we can really measure the thickness change of these electrodes, operando. Now, 1 milliamp hour per square centimeter lithium is roughly 5 micron, sodium, 9 micron, potassium, 17 micron. So potassium is in principle the nicest for a dilatometer. Huh? And that worked very well, so both together measured really in a nanometer resolution dilatometer the thickness change of a potassium anode, and this dotted line is what you would expect from Faraday's law. Well, you know exactly how much charge you draw, so you can calculate how the rate of thinning of your electrode, and what you see here is the thinning is less. Why? Well, because we create pores. And so while the resistance of the electrode remains constant, pores are being created, and these pores can be followed simply by a dilatometer. You see that by a dilatometer experiment. From the very beginning, we form pores because we operate at rather low pressure. And this changes, of course, when we go to higher pressure. So this would say a new technique into these metal anode studies. And with that, come to the end. Everything, the success of any of these technologies will later depend on the success and the cost of LFP cells made, produced by China. That will decide on everything. SSB cells can be high energy cells, and solid sodium cells may enable true high power cells because we have even better electrolytes than in the case of lithium. But at the end, that also needs change in paradigm for production. Maybe we have to work on cylindrical solid state batteries rather than just stacked cells. And with that, come to the end. Thank all the funding agencies. And of course, without the POLiS cluster, would not have, I would say, gone so deep into sodium and the other stuff. Thank you for your attention.